And beyond. This is day 14 of my DSA series. Today I will be covering question number 278. That's first bad version. It's an easy question, so let's dive right in. So the question states you are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality checks. Since each version is developed based on previous versions, all the versions after a bad version are also bad. Suppose you have n versions, 1, 2, 3, all the way up to n, and you want to find out the first bad version, which causes all the following ones to be bad. You are given an API bool is bad version, which returns whether version is bad. Implement a function to find the first bad version. You should minimize the number of calls to the API. We have our first test case, n is equal to 5, bad is equal to 4. Output is equal to 4. So explanation, call is bad version 3, we get false. Is bad version 5 true? Is bad version 4 true? Then 4 is the first bad version. N is equal to 1, bad is equal to 1, output is 1, and the constraints are given, so bad goes from 1 all the way up to less than equal to n, and n is basically less than equal to 2, and 2 to the power 31 minus 1, and this is a question that we're dealing with. So I'm going to copy this test case, and I'm going to try to explain it through the test case. So let's dive into the solution. So let's read the question again. We're basically a product manager, and we're basically developing some product. And if one version of the product is bad, then all the following versions will be bad. We just have to find out the first version that is bad. And in order to check whether the current version at hand is bad, we have this API, or that's basically a function bool. It is bad version, and it returns true if this version is bad, and it returns false if the version is good. So we just have to return the first bad version. So let's look at this test case. N is equal to 5, bad is equal to 4, output is 4. So let's sort of understand what happens in the background. Hopefully this is visible. So I'm going to take an array of size 6. And why am I taking an array of size 6? Just so that we can balance the indexes. Like the index and n's value would be the same. You can do that. Or the other ways, let's just consider an array of size 5 for now. And the first value would be 1. So for index 0 would be 1. So let's take an array. Now this is the array that we have. Now what we're going to do is we're basically going to make partitions. So 5 entries 1. Basically have 1, 2, 3, 4, and 5. This is array, and we're basically gonna have 5 versions because that is mentioned in the question. So this would be version 1, this would be version 2, this would be version 3, this would be version 4, this would be version 5, and the indexes would basically be 0, 1, 2, 3, 4. So we can say that index plus 1 gives the version. Now the explanation is given, so it's going to call is bad version for 3. So let's suppose we start off at 3. I'm going to take a simple pointer that starts off at 3. We make a call, we get false. That means this version is not bad. This version is not bad. So we know that the future versions the future versions won't be bad. So 4 and 5 okay, sorry. We don't know that the previous versions are not. We know that the previous versions are not bad, because if one of these versions was bad, we would know that 3 ought to be bad, because once a version is bad, all the following versions are bad. So we know we don't have to search in this search space. So for now, let's say we just ignore this search space, because we know when a version is bad, the future versions are bad. So if this version was bad, we could say that 4 and 5 is bad. Now, if 2 was bad, we could say that 3, 4, 5, all of them were bad. Since 3 is not bad, we can definitely conclude that the elements before them could not be bad, because if they were bad, 3 would also be bad. So we move ahead. Now, suppose they called it for 5. They called the function for 5. They call the function for 5. We basically get true. That means this is bad. And we have to find the first bad version. So we know we'd have to search before 5, correct? We'd have to search for elements before 5. We'd have to search for elements before 5. We've already looked at 3, so yeah, I can also cut that off. Now there's only one element left, 4, we call it. 4 basically returns true, which means that this is the first bad version, because 5 was bad. So we'll have to check for elements before 5 and check whether they are bad. So 4 is bad, we get true, so we can return 4, because we've checked out all the other 3 elements. So I'll cut this off. So from this approach, something you probably understood is that we are kind of dividing our array into 2 parts. Like You can say that, right? We basically looked at 3. We saw that the 3 wasn't bad. So we know that the elements before 3 can't be bad, and 3, it isn't bad. So it can't be the first version. So we look ahead. Then we looked at 5. When we looked at 5, we saw that 5 is in fact bad. So all the elements after 5 will be bad. So they won't be the first version. So by default, at least 5 must be the first version or an element before it. So we saw that 1, 2, 3, they cannot be the worst version. The first bad version. So we go at 4. We check out for 4. 4 is in fact bad. And since we've already searched all the elements, we know that 4 would be our answer. That would be the first bad version. So the brute force approach that could come to your mind is simple. What if we just run through this? Run through our entire array, run through all the versions, check if they're bad. So to check the version, we do index plus 1. So we check is this bad, we get false, this bad, false, false. Once we get true, we can return that. The only issue is that we have to minimize the number of calls to the API. So how can you do that? Now we know one thing, that our inputs are sorted because like they're going according to version, right? So 1, 2, 3, 4, 5, they're going to be in ordered line. So whenever we have a sorted input or sorted array, you know that the best approach that we can have is a binary search approach. And if you don't know what binary search is quite simple. We're basically break down the array into smaller portions and we search in that given portion. So if you don't have a basic idea about binary search, we basically take a low pointer, it points at 0, we take a high. Then what do? We find a mid. So 0 plus 4. So we take low plus I divided by 2, 0 plus 4 divided by 2. So this is our mid element. When we are doing normal search, suppose we wanted to search for 2 and use binary search for it. So we start off with low, high, we find mid. Mid is basically equal to 3. Now are these values equal? They are not equal. Now since 2 is less than 3, we know that we can't search ahead of 3 because we know that our array is sorted, right? So we'd basically search through this portion. We'd search through this portion of the array that we have. That is where we're gonna search. Now how would you do this? You just take high, you move high over here. So mid minus 1 is high. Now if we do 0 plus 1 divided by 2, you basically, what do we get? We get 0 plus 1 divided by 2. You end up getting index 0. So you look at this. Now 1 is smaller. We have to look ahead. So in order to look ahead, we basically do mid plus 1. So low comes over here. 1 plus 1 divided by 2, it becomes 0. 1 plus 1 divided by 2 becomes 1. So we look at this index. That is our answer, and we are good to go. And we can continue this process till low is less than or equal to high. That is the main you can say the main logic behind binary search. So we're going to use something similar. So let's take a new array. Now hopefully you understood the binary search approach, right? Like we hopefully understood what binary search is, and if you didn't, you should probably watch a couple of videos on binary search because it is an important concept. And there are 2 main ways to do it. We can have a recursive method and then we can have a iterative method. I basically showed the iterative method in a way. You can say that I basically showed how low and high moved, but we could do it recursively. It's quite easy, so hopefully when I code it, it makes sense to you if you haven't actually dealt with it before. So now let's take our example and show how binary search is going to be used to solve this question. Okay, we take this 1, 2, 3, 4, 5. So this is what we have. So we are taking that same case. We basically have 1, 2, 3, 4, 5. That is what we are taking. You can write down the indexes 0, 1, 2, 3, 4. We take this, and now we're going to apply binary search. So I'm going to use low and high. So low is set to 0, and high is set to this, right? So first of all, we look at mid. We find mid. So we know that mid would be this element. This element would be mid, right? Mid would be right smack down in the middle. So what are we doing? We're gonna call the API. We have to basically call the API to find out whether a given version is bad or not. And the logic, I'll explain the logic first. So the logic's quite simple. When we encounter a bad version, we keep on searching for whether there are any more bad versions behind it. Because if there are any more bad versions behind it, that would be our first bad version. That is all that we're going to do. And if we find that a version is good, we search ahead because we know that none of the versions before this could be bad and this version won't be bad as well. So we search ahead. That is all that we have to do. So let's say we have low, high, and mid. We look at mid. We call for 3. So over here we saw that 3 is false. So what did I mention? Since 3 is false, we know that the elements before 3, they cannot be bad. So we're essentially ignoring them. So you can say that we're just ignoring these elements, and we're also ignoring 3 because we know 3 is not bad. And since we know 3 is not bad, any version before it won't be bad. So we can say that we're going to ignore all of this, and now we're going to search ahead. So in order to search ahead, what do? We do low is equal to mid plus 1. So let's consider mid. We want to move it away for some time. Right now, low is going to be considered mid plus 1 because we have to search ahead of it. Now we call 4. Now what do? We call mid. Now what's mid? 7 divided by 2, that gives us 3. So in this case, we basically get true. We basically get true that this is a bad version. So all the versions after it would be bad, and we've already discovered all the elements before this. So we know that this would be our first bad version. And that is in short all that we have to do in this question. If we find that a given version is good, we search ahead. If we find that a given version is bad, we look behind. Is there any indexes we haven't used yet? If that is the case, we're going to go back again and try to search. So in this case, mid would be over here. And since, like I mentioned, we basically said that if a version is bad, we're going to look at all the versions before it. So mid would be, now in that case, that basically means we are going to move head to mid minus 1. So head moves from mid minus 1. Head is less than though. So we know that our loop's going to end anyways, and we have gotten our answer. So now let's try to code it up. Hopefully things did make sense. We're using a simple binary search approach. And I'll just say it again. If a given version is bad, we search for all the elements before that version, and if a given element is good, we search only ahead of that given element, since we know that the elements prior to this element and this element cannot be bad in any case. So simple. We're going to take int left, set it up as 0. Int right, we're going to set it up as what? And set it up as n. N's the size, right? So basically have 5. 5 is the size. So n minus 1, that is what we're going to set it up to. So while left is less than equal to right, instead of left, we can have low and high. So let's just say low and high. Low is less than equal to high. So we're going to find int mid first. So int mid is basically equal to low plus high divided by 2. Now, in some cases, low plus high divided by 2 might give an error because like the number goes out of bounds. So what we're going to do is, first of all, we can have a variable long that's going to be used to store our answer. And instead of doing this, we have another cool method. So we can basically do low plus high minus low divided by 2. So if we convert this, what do we get? We basically, if 2 goes over here, we get 2 left. 2 low plus high minus low. So high minus low divided by 2. And why am I doing this? I'm just doing this so that we don't get an out of bounds error. We don't want the integer to be out of its range. So this is why we're using this shortcut. We find mid. Now we look at this. Now we look at mid. So we look at, so we're going to make an API call. So we check if is bad version. Is bad version. What do we say? We can say m is the index, so m plus 1, correct? Because we saw that index plus 1 would give us the element. So we find mid, we do is bad version m plus 1. If that is equal to true, what do we do in that case? If it is equal to true, we moved high is equal to basically mid minus 1. That is what we do. If we get true, search for elements before it, and if it's not true, if it's false, we can do that low is equal to mid plus 1. Low is equal to mid plus 1, and over here we can store the answer would be equal to m plus 1. We're assuming that this is the answer, and we're just storing it for future reference. And now we can just return the answer, and that should basically do things. So we take L, starts at 0, H goes to the last element, so n minus 1, we take long answer. If left is less than or equal to low is less than equal to high, we find the mid, so we use this formula. We check is bad version m plus 1 equal to true. That means if it is a bad version, we have to search for all the answers before it. So h is equal to mid minus 1, answer becomes mid plus 1, we store it. In the other case, we're just going to do left is equal to mid plus 1 or low is equal to mid plus 1, and we are going to return our answer, which could be in long or it could be an int. That won't really be making a big difference. So that is all that we are gonna do in this case. So we take int m, we find the middle element, we call the function. If it's true, we basically move h, then we basically store answer somewhere. Then what do? We call our else. So if is bad version m plus 1, if that is equal to false, meaning that the current version is not bad, what do? We can basically only search for all the elements that are after the current element. So that is why we search in the right half. So that is pretty much it. So whenever you're doing a binary search, you just have to understand what's the right half, when do we go into the right half, what's the left half, when exactly can you go into the left half. That is the main question that you should be asking yourself. when do we go where. That is all that you need to do, and you can also take care of this. So as you can see, I got the answer, and this is pretty much the solution for it. You can try a uh, recursive way. That wouldn't really make such a difference, and in such a case it doesn't really matter. It's always better to first understand the iterative way. So I won't be doing the recursive way, and if you feel like you want that, you can write that in the comment section down below. I'll provide the solution for that. So thank you so much for tuning in, and see you tomorrow.